Craft Studio. The fuck is that? For fuck's sake, Twitch. Okay. Going for death, gents. Simple enough. Let's see if this actually works. And let's try it in an environment that is not a desert of some kind. Actually, let's get a baseline first. Let's comment this code out. Okay, so after fires, we then calculate death. But for now, let's comment it out. Oops, that's right. We're in Python. How did Python commenting work again? Like this, maybe? No? No? Okay, whatever. All right, so let's start with something we know is a bit more stable. So first off, go with maybe 500 years. Maybe temperate forest. That's interesting. Okay, so we got upwards of around 47. Killing trees with old age so that they settle in on a more rational equilibrium. Okay, so this is how tall our forest was without any natural tree death. Obviously, there's fires causing deaths. Let's snip this. Stash it. I mean, we could get some actual metrics and record those instead, but we'll just eyeball it for now. Okay, so our temperate forest. Really, grass. I need to buff grass, I think. Grass is not rebounding the way it should. We'll sort that later. I can't buy. Broadleaf is a type of tree. So, think like maple tree. Right. So only a leaf that's big, flat, leafy, collects a lot of sunlight, but is vulnerable to, but takes a good bit of investment to create And so it thrives in certain conditions. Right, versus conifers, which have thin needles that aren't shed. Broadleaves like areas where they can get lots of sunlight and have nutrients necessary to maintain leaves that's expensive to create. Okay, so temperate forest. All right, so we have a little snip of what we're interested in. Mocha, how do you comment out large chunks of Python code? So in C#, you can do this, right? Uh-oh. Did I not have my colons? Here we go. Interesting. Very interesting. So, our two plots. Oh no! I trimmed out the units. This was 40. This was 48, 47.5, something like that. So you can see we have some divergence here. Because conifers are growing slower. Because conifers were growing slower, they settle on an equilibrium canopy height that's lower, in this case. We may want to have alternative death probabilities. But I don't know, maybe not, we'll see. That may be one of a conifer's advantages, longer life. Let's Google that. Do conifers live longer than other trees? Because if you think of all the largest trees in the world, like sequoias and stuff like that, it's all coniferous. Not the best source here, but let's get some. Conifers invest in growing long-lived leaves. Deciduous trees put their sources, blah, blah, blah. Overall leaf area is so much greater than the short-lived leaves. Yeah, blah, 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 we know. We just talked about leaf strategy, but we want... Deciduous leaves have greater photosynthetic ability, as we know. Nutrients are in short supply. Evergreen habitat may be more efficient. Yes. Let's look at specific trees. I don't know though. Because you look at like slash pines and sand pines in North American South. They don't live super long. Well, we'll worry about this later. Anyway, this has definitely created more of an equilibrium. I'm curious what this trend starts to look like when we stretch it further out. That's interesting. This is our temperate forest, really. I was expecting that tree death... Oh, I see. So... I don't think I'm doing this right. Fuck. Is it 4 quotes? For fuck's sake. I guess the problem is my IDE wants to keep sticking more quotes in, which is really annoying. There, right. Okay, so let's run it again real quick. Oh, how weird, man. Something's wrong. Something's not right here. I made a mistake. Yeah, I had to have made a mistake here somehow. Because we get very different. This is much more in keeping with what I was aiming for, temperate forest wise. So I think we got the canopy math right, but I think something is wrong with. Oh, that's interesting. I didn't even apply the depth value. Why was I getting those weird Oh, interesting. Oh, very interesting. Okay, so see, now we get this, right? Weird. Here, snip this. And we'll do a side-by-side comparison. Round again. Oh, Isdar. Okay. Some of the shorter lived. We'll read that in a second. Let me make sure Okay, so canopy, we're not concerned about at the moment. Vegetation prevalence. So why? Oh, I know what's going on here. By killing off the canopies, so even though we didn't apply tree death specifically, we were applying sort of the effects of death on canopy height, because a taller tree is going to end up dying from age-related issues, or just stochasticity not related to large-scale disturbances. Okay, so termite infestation. And what was happening is because conifers are generally slower growing anyway, it was causing the net decline in their canopy height, which then meant that they were smaller trees not producing as many seeds, and so that depressed their numbers. Which is, I guess, what's supposed to happen in the model, so that's not unusual. Question is, what's going to happen when we start adding uniform death to everybody? So tile. Well, I can tell you one thing that's going to happen. Tile broadleaf half. There's just one thing I'm concerned about when we do this, though. I'll explain in a minute. Minus equals broadleaf death. The thing I'm concerned about is this could actually prevent our forest fires long term. Tile conifer. We don't want tile broadleaf, tile conifers, conifer death. Oops. Blah. Right. Yeah. Something's screwy here. explain what's going on in a bit. You know what? Maybe we only really need to worry about the canopy death chance. We can assume it's implicit in the growth model. I guess. I'm curious. Okay, so let's just comment out all of this stuff. We'll keep the canopy, the downward canopy pressure. Okay, so Mocha, let me explain what's going on. So, here is a graph of canopy height for conifers and broadleaves in the same tile. You can see our broadleaves. There's gyration over time. Some of it's just from internal tile stochastic issues like I talked about before, termite infestations, whatever. But then some of it's also the result of forest fires. You can see down here we're logging out all of the fires. Huh. Why are there so few fires now, though? Well, I guess... we have I guess there's quite a few fires. There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Yes, there's maybe about 25 fires, but that's over 500 years. One every 25-ish years. Anyway, so yeah, that's canopy height. We'll have to retune that. This is per capita growth. You can see there's seasonal variation for different types of plants. And then here's our vegetation prevalence over time relative to one another. Here's broadleaf trees, which are like your maples, conifers, which are like your pines, shrubs, grasses. Why is this in Python instead of C#? Because I needed to learn PySpark for my job, and that was going to take extra time, but I didn't want to take away from Song's time, so I figured I'd just learn Python while doing Song stuff. So I just plugged in a few Python libraries to graphically represent this stuff. Alright, so we have a slight issue, and that is we're getting roughly, I guess, the right distribution. So what's nice is we have this kind of divergence between canopy height without one type of tree going extinct. There's not enough variation over time, though. We don't have that nice species turnover effect. And I think that's because we don't have the occasional dramatic destructive fire taking place. Interesting, we do have long-term deviation in canopy height, which is cool. Let's see how this looks in other environments to see how stable the model is. Right now, I would say that the model is like almost too stable. Because we had that nice effect previously where you would have a period where conifers were dominant, but then it would shift, or at least be more prevalent. So let's switch up our biome type. Let's go with boreal forest, see how that looks. If we have a lot of broadleaves here, then it's screwy. Okay, so that's cool though. That's cool. So now we have realistic boreal canopy height. Downside is we have an environment that's way too stable, so no disturbances. So conifers dominate, which is what we want in Taiga. We have a few broadleaves, which is what we want in Taiga. But there's no disturbances. Oh yeah, let's see what, I meant to catch up on what Isdara was saying. Some of the short-lived trees include palms, which can live around 50 years. The persimmon has an average lifespan of... Yeah. I think there's actually some olive trees that have been around for thousands of years or something ridiculous. And the black willow will probably survive around 75 years. On the other hand, Alaska red cedar can live up to 3,500. Giant square is 3,000. Wonder what makes one tree species last longer than another. Basically the same standard that you would apply to animals. From a natural selection standpoint, can you justify investing a whole bunch of resources into living longer if something else is going to kill you off anyway? And so sometimes it's a better reproductive strategy just to go for broke, reproduce like crazy, and accept the fact that you're going to die, and then just let your body fall apart. Like, that's the strategy of cephalopods, right? They're just like reproductive ballistic missiles. It's like, get to adulthood, reproduce, and then all die at once after. There's literally a term in biology for that called simulparity. And you have seasonal plants that do the same thing, which will grow real fast. A lot of insects do it too, grow real fast, and then spend no resources whatsoever in investing in long-term survival, produce a bunch of seeds or a bunch of larvae, and then just die. This is so funny, Mocha. All of human history. You made a funny. So we have an issue here, and that issue is previously we were probably inappropriately relying on progressive growth to eventually trigger wildfires, which sometimes they still do, but we haven't, in our disaster model, we have not accounted for what Calandial has added in the world climate system, which is variation in rainfall. We sort of did it in a generalistic sense, but it's not nearly pronounced enough. So I think what we're going to need to do is we're going to need a little random factor up here that causes variation in rainfall conditions, so that occasionally we'll have a period where where we have dry conditions. Oh, it looks like we actually did have some extremely light wildfires, but not nearly enough. I like the equilibrium here, though. From year to year or season to season. There's variation between seasons now, but deviation from the average right now, and that's something that happens in the climate modeling game. It just doesn't happen here. I just took snapshots. So what we can do this fairly easily, I think. Yeah, dry year, moist year. So having variation in that fashion is going to create the risk of wildfire in both senses, right? So let's say you have a wet year, and you're already pushed against the carrying capacity of the ecosystem. Carrying capacity is not the right term. So if you have a wet year and you're already pushed near to a point of fire, there's already a lot of vegetation, you're already using up most of the water, then having a wet year actually artificially pushes you above the amount that the ecosystem can tolerate without a fire, so that then if you go back to either a wet year, if you go back to a dry year or just an average year, risk of fire is increased, and so you get it from both sides. And so I guess let's just go ahead and add it in now, and we can tune it as necessary. So what we want to do, theoretically we could do it for temperature too. I don't want to get too complicated. Yeah, that's a great point, Captain. is you can, I mean, and that's how the Dust Bowl got started in the United States, right? They went out, a bunch of farmers went out to the western states, the low grass prairie during a wet year and said, hey, this is great for farming. And they had, maybe a decade of good farming, and then boom, they got screwed because once that abnormally high rainfall went away, they were overtaxing the land and they caused mass erosion, and the rest is history. All right, so seasonal rainfall. I think what we can do is add in a random factor up here. Up here? Let's just express what we actually want. How about that? Where's the right place to put it is what I'm wondering. Well, we can put it with disturbances, right? What's really interesting about what happened with the Dust Bowl is it was like they knew better. Federal land surveyors knew that was a potential outcome and warned against it, but John Deere lobbyists thought otherwise. Alright, so we want variation in rainfall. Ideally, we want smaller ticks up and down from season to season, but we also want larger ticks. But we also want larger periods of severe drought or significance. Right, so a little bit of variation from year to year, and then occasionally significant variation, potentially for longer periods. Yeah, and that's the role that wetlands play too, Captain. Right, it slows down the water, and that's something we actually already have in our model. So if you decide that you if you end up destroying all of the upstream wetlands in the headwaters of your river, then all the water, once it rains, just rushes down the river, swells the banks faster, and then just wrecks everything. And that's something that's already in the model now. So when we actually calculate flooding destructiveness, then we'll have those variables in place. Alright, so how do we want to do this? We want to get our little random... Where the hell is it? Aridity. Rand. Where is... Here it is. What would be nice is if we had some kind of self-regulating... It's funny, this is just supposed to be the basic model. I'm like, if we had some kind of self-regulating. No, if we had some kind of regulatory mechanism for variation in rainfall, so that when you deviate from the mean then you tend to return to it. Let's not get too complicated. Let's just do this. Start with basic positive or negative deviation factor. 1 second. What do you mean, Isdar? Wouldn't vegetation just die from lack of water? Okay, so we can do something easy like, right. Yeah. Well, I mean, so oftentimes what happens when you have prolonged droughts too is lack of water will cause some of your woody plants to die, and then they just accumulate on the forest floor or in the scrub as like tinder. Yearly deviation. Okay, so what we can do now is we can just have this basic yearly deviation factor. I guess we should probably test this first. Seasonal rainfall equals season rainfall times yearly deviation. This will probably give us a few more fires. Let's just see what happens for now. So this is boreal. Or not. It's kind of surprising. Am I missing something? I may be. Ah, yes, I am missing something. I was wondering, like, why the fuck is this not doing anything? Alright, so the problem is we are applying the changes after we've actually calculated how much water is available. Water movement contribution. Okay, so we just need to do it up here. Temperature, soil factor, this should be independent of water. Available nutrients should be independent. Why did we comment out permeability? I don't know. Whatever. Put it here. Okay, now we should see an effect. Yes! There we go. That's troubling now. Well, maybe... Well, we only have one small period where the canopy... Well, broadleafs are taller here. Okay, so now we actually have some significant fires. The question is this actually a longer term trend, I wonder? Still, we have fires that are pretty... Okay, we still have conifers dominating in the taiga. Let's run this again and see if it's a long-term trend. It does appear to be a long-term trend. Oops, no, cancel. And what's odd is let's log out how much water we have. Well, yearly deviation, seasonal rainfall times yearly deviation. Let's make these let's just make this really radical and see what we get. I may stream on Sunday. Okay, right. So we got in the canopy, just got totally squished. Right. So here we see we have way more way more variation, and now you can see the wildfires are like really dominating. What's interesting though is the prevalence is. We don't really have any long-term extinction. That's interesting. This is good. This is moving in the right direction. Okay, cool. So really what this tells me is what this is telling me is we need that larger spike, that pulse of bad weather. And what? All right, let's see. Try a significant deviation here, and what we'll do is it won't. What's the best way to do this? Significant deviation or mean form. Oh, let me specify that we want to float up here. Right, is that what I have down here? Yes. Okay, significant deviation chance. Now what we can do is if significant deviation chance is less than 0 points three. Drought. I now know that. So really what I want to know is whether different classes of trees, some classes of trees tend to live longer than others, as opposed to just specific interesting outliers. I mean, it's tricky because, the evolutionary pressure on a tree to live long depends very much, as I mentioned earlier, on whether something else is going to kill them off anyway. That's kind of like why humans get cancer and other animals would get cancer at certain ages. It's like a pre-modern human wasn't generally going to be living naturally to a point where they would get cancer anyway, so there's no selective pressure to invest a bunch of resources into making sure you don't get cancer. Yeah, it's dark. So, My gut instinct is that conifers live longer, but I could be wrong. Significant deviation chance 0.03. In this case, we'll get a droughts, else if I forgot how to do else ifs with Python. Else if significance is greater than 0.197. Epic parentheses. I'm not a Python person. Significant deviation chance. Oh, that's right. I'm sure I have another else if somewhere here. Oh, or not. Just if. Alright, so here we go, what year? How do we actually modify the values? Okay, I know what we can do. Seasonal rainfall, we can just modify it. And then we can just stack it with whatever that yearly deviation is, and that'll give us our, our random variation. Yeah, this is either increasing or decreasing water availability. By the way, I had a plot. Yearly deviation is applied down here as well. Right, so it's going to end up either... It's gonna either modulate it upward or downward. But I was hatching a plot. I have an issue right now with the water flow model where I haven't been able to recalculate water movement on tiles based on seasonal variation. I've been really wanting to find a way to make it happen. That way you can have situations where you're not only dealing with droughts as a result of direct rainfall where you happen to be standing, but also downstream effects of water flow. Conifers are generally hardy plants that can withstand extreme growing conditions. Conifers are also considered the longest lived woody plants on the planet. But that is their sort of long-term history. It should, Sabatkins. The problem is right now it doesn't in the way that I would like it to. The main issue is the way water flow calculations are done is every tile in the world is checked to see if it passes water to a lower tile. If it has lower tiles, it then passes water downhill based on sort of the differences in elevation between tiles. But then every tile that receives water is added to a list, and then the process is looped to repeat again for every tile in the world that receives water. And so then it goes again. And so effectively what it does is it means that we end up checking every tile, like we don't check every tile in the world every single iteration, but we end up checking maybe 100,000 tiles a few hundred times. And it's just it's really clunky. And so what I wanted to do was, after the erosion model is over, soil, evaporation, etc. I'm trying to find a way to speed it up so that we can do water flow every single season, but it has to be sort of performant, right? Yearly deviation, significant deviation chance. Okay, so let's... Let's go 1.5, that's fine. Okay, we apply yearly deviation, but now we need to... Well, okay, so we applied here. Alright, so let's see what happens. Yeah, so the issue right now, Sabatkins, is basically we run water flow once and then do a bunch of inferring. And, and then we construct the water bodies, etc., etc., etc. But what I'd like to do is to be able to come up with a compromise solution where we can run the model every season. And once we form sort of water bodies, we can, instead of having to make the water run from tiles all the way to the ocean, as soon as it hits a water body, then we can use water bodies as objects to pass the water around, and that'll speed things up too. But what I really need to do is redo the water model flow, in which we create a global list of tiles from highest elevation to lowest elevation, and then just go through every single tile in the world each time. It'll be a heavy lift to make that vector, but then, or to make that list. But once it's made, then we can just go from top tile to second highest tile to third highest tile, and then just go down the list and pass water, and it'll literally cut down on the number of checks we make by like 500 or something. And that should allow us to get the water flow going real fast. I mean to get back around to it, but I want to get vegetation to a point where it's reasonably complete and plugged in. All right, so let's see what happens here. So previously we had a total intensity of fires of 21.7, I think. There we go. So we have more fires, lower canopy height. As a general rule, there are more species of long-lived broadleaf trees than conifers. Okay. Thanks for answering that question for me. Yeah, that's kind of what we really need, but it's sort of a casual observation. And the important part is that it just sort of challenged my assumptions, right? Okay, so we have an issue here. The issue is, I feel like our conifers rebound too quickly. I feel like almost, yeah, we really need our grasses and shrubs to grow faster. So I like, if we look through the list of fires here, we can see we have some that are a good bit sharper. Right? really get too destructive, which I guess is okay. Oh. Oh, oh. Okay, good. So we do get a few, 100-year fires, so to speak. Cool. Okay, and we saw grasses come to dominate for a period of time. That's cool. The issue I see is let's do this. This may just look like gibberish, but let's push this trend out a few more thousand years. That's cool. We actually have periods of pretty high canopy. Periods. Okay, interesting. Oh, wow. Yeah, wow. So we had, a succession reset here. Interesting. Occasionally we have these 1,000-year fires that reset things. What I find interesting is we actually had a period where broadleafs and conifers had rough parity. And then they go back to sort of their historic level, and then boom, there's a period where they're no longer prevalent. What's really interesting is we have a period where shrubs dominate. That's fascinating. I do wonder whether it takes too long, though. Ouch. Did we have broadleaf extinction? I think that's a pretty good model. Whoa, okay, 160 fire intensity. Let's see if we can identify the 100-year fires. I don't see anything that would indicate that. Although it seems like right out of the gate we had a pretty nasty fire. At a category 7, 5, 7. Oh, and now that our canopies are shorter, these fires are going to be more destructive to trees because their crowns aren't going to be above the fire anymore. So even though the fires aren't as big as they were previously in the model, they're going to be more destructive just because the trees are stuntier. Okay. Well, this is interesting. I really feel like our... This is what bothers me, though. Like, such a... like, how sharp is that growth? It looks pretty sharp. Let's look at our pop history. Model for triggering fires. The fires, I mean, it's pretty intuitive, right? It's how much mass of what your plant mass is relative to available water, which is influenced by seasonal variation of rainfall. Okay, let's just go ahead and auto sum this real quick. Huh. interesting, actually. Oh, that's interesting too. What's going on here? Alright, so we were pushed against the wall for a while. What's weird is it seems like grass, like, not rebounding nearly as quickly as it should. Because here we have shrubs. Well, shrubs are pretty slow growing. Here we have grass. Here we have conifers that were added. Huh. Oh wait, did we add headers here? Broadleaf. Okay. Oh yeah, we saw our broadleaves like basically annihilated. Okay, so what, we had a fire someplace recently. Boom. Yeah, here was the fire. Wiped out pretty much everything. But here's what troubles me, right? I feel like we should have had a rebound in the forest that was faster. Maybe not. At least it feels like grass should be moving in to grow much faster. And shrubs. Especially given that now there's no crowding factor preventing them from growing. You know what? Maybe that's what we need, actually. So we have a crowding factor in there in which grasses and shrubs are sensitive. So, right, grass crowding factor. Here's where we calculate it here. I mean, it's not determined. I mean, in theory, everything is deterministic, but like, yeah, there's nothing is guaranteed. You don't meet a threshold and then suddenly, boom, everything goes up in flame, because there's all kinds of other sort of variation involved too in forest fires. Like, there needs to be something that actually starts it, right? And so it's like, obviously, if you have a wet season and not many plants, you're not going to have a fire, or it's going to be outrageously improbable. And if things are dry, then you have too many plants, then you're probably going to be much more likely to have a fire. That's really how the model works. It's intuitive. Feel almost like we need a niche saturation for shrubs and grass too. We could probably add that in. Okay, so right. Okay, so I think I know what we should do. We just need to jack up our base growth factor for both shrubs and grass, because they're facing crowding and they're replaced through competition. Okay. Total intensity of 1. Now this looks chaotic, but keep in mind it's over the course of 2,000 years. I'm a bit surprised that the grasses don't move any faster. Let's just see what happens here. I mean, the trigger is just a check. It's just a check of water availability plus some random factors. I mean, usually, like, things like lightning strikes can start fires, right? Okay. Grasses just are not happy. Let me see something. First off, let's get our averages here. Yes, I'm sure I don't want to save. Okay. Did I capture rent? Okay. I had a little formula down here that captured average figures, grass average. Okay, did I not print them? Print, yes. Oh no, here they are. Okay. So let me run the model for like 10,000 years or something. Get the averages, plug them in, and then I have to do it for 5,000 years. Fire intensity, years of growth. Okay. So what we want to do now is plug those numbers in. Right now we're doing boreal forest. Oh god. Wait, how many fires did we have? Fire count 183. That's a decent fire every 27 years. That seems about right, to be honest. And they're reasonably destructive, and then occasionally have one that's really nasty. Seems about right to me. Okay, so boreal grass average 2342. Tile shrubs 13811. Tile conifers 32087. It's funny how the canopy height is so much lower, which is fine. Isdar, if you're out there, can you by any chance look up the average canopy height of a takeoff? Oops. Thanks, bro. Okay. So now, let's go ahead and tune the number of years that we're running the model for so that we can actually see some resolution. So 400. That's cool. Sometimes we do get canopy heights as high as 20. Looks like we had maybe a wet year there. I'll be right back, by the way. Hold on. So here's the thing that's troubling me, I guess. So there's an issue in the model right now. So the grasses are getting crowded out too much. Although maybe not. Let's do this. Let's log out our crowding value. Let's tune. Let's go ahead and let's do 100 years. See what 100 years looks like, and then we will. Okay. Oh God, why is grass blow so much? It's gotta be the crowding issue. So the grass has got two things working against it at the moment. It's in a nutrient deprived place. And it's being crowded more than shrubs. So this is Tega at the moment. How do plains and savannas maintain the grass? So on plains and savannas, you have a lot of microfires, right? But also because shrubs do very well in places that are mineral constraints, they end up outcompeting grasses too. But where you have higher temperatures, you also have higher soil temperatures, which means a more robust microbiome in the soil, which means more mineral nutrients. And so then grasses do better there as well. Grass in general should do better in situations with microfires. But what should be happening here is we should have a fire like this. We should see grasses fill the vacuum way faster. Usually, if a grass's root structure is preserved, it can rebound really quickly. So I'm wondering if what I need to do is just have a variable that keeps track of what the grass was before it got burned, so that it can rebound faster. But if it's at a low level, if it's at a low baseline already, like, is it really gonna make that much of a difference, you know? Yeah, growth rate, depending on the plant type, there's a crowding factor, right? Grass can get crowded out very easily. Actually, let's do this. Let's look at our spreadsheet again. Oops. Yeah, that's part of the issue, right? And I mean, Epic, another thing too is that grasses famously have seed banks too. And so they can literally drop a bunch of seeds down, and even though there's no place to go, they can go into this hibernal state almost, where they wait for a fire, and then they're there, ready to grow. And so previously what I had in the model is I had a baseline of like a seed bank for grasses so that they could grow really quickly in the event of a fire. The issue is I want to be able to account for overgrazing and things of that nature later on. And so there's this issue where if a grassland is abused and overgrazed over and over and over again, you actually and it's not being depleted as a result of fire or pulses of grazing animals like roaming herds. If you overgraze indefinitely, then you actually exhaust the seed bank and you don't have that rebound effect. And so it's like, I probably shouldn't be letting that define my model too much at this point, but it is kind of important later. I'm curious though. Let me let's auto sum here. Oops, formulas. Yeah, see, when you've got grass that's this. Yeah, we could do that, Epic. We can come up with something. Number of various taiga areas with their average height and got 20 to 25 meters. Okay, that seems about right, Isdar. Thanks. Yeah, that's what I'd like to do long term, Sabatkins, because then it's also, you'll be basically, you'll be altering the albedo of the lands, but then you'll also be altering evapotranspiration too, which means less water retained in the atmosphere, right? Or less water. One of two things happens, right? It either just drains into a water body before it can be released in the atmosphere and drains into the ocean, or it just goes into the soil and disappears into the aquifer, at which point it doesn't return to the atmosphere too. But yeah, modern desertification is definitely influenced heavily by overgrazing even now. And of course, like Cithril says, sort of longer term trends too. Okay, so let's just do this. Go away. I don't need to commit anything. Go away. Okay. 500 years. Let's just go ahead and put in our seed bank. One thing we can do in the future is possibly infer the seed bank based on conditions too. Right, so here we have a seed bank only of 1,000. Let's see what this does. Let's see if this allows our grass to rebound. Okay. That happens. I mean, sure. Why not? Let's run it a few more times. Maybe make the value a bit more sane. But then again, I mean, this is what you see, right? Alright, Taiga Meadow. Right? Is it's common to have a fire and then poof, then you have these areas that are meadows for some period of time, and then the trees have to re-encroach, right? So I'd say that's fairly reasonable. Let's alter the seed bank We can always make these alternative variables too. It's a compromise. So Skizzer, it's a compromise between what we've witnessed in our reading and what we need, because there's no way that we're ever going to possibly capture all of the nuance, that you see on the ground floor, and so it's really a compromise between getting the end result and replicating the process. Apparently we had some fires of doom in here that just annihilated everything. Total intensity 33. Oh no, they didn't annihilate the conifers. Never mind. Seems like there's too many broadleafs here, but... Oops. That's not what I wanted to do. I didn't want to make the base growth 50,000. Thought that made things look a little weird. Okay, that looks a lot more sane. Alright, so you have periods of grassiness. I think that's reasonable. Broadleafs are generally okay. Yeah, I think that's pretty good. Let's see how this holds up in other environments. Yeah, and part of the considerations too is like the sort of cast your imagination into the future and think like, okay, how does this influence gameplay too? And so it does involve a certain degree of feeling. And you're working with memory constraints and computational constraints, CPU cycle constraints. And so there's a lot of compromising that has to be done. Alright, let's change up our environments. First off, let's see if our average numbers are appropriate here. Boreal. Okay, so we still have not a lot of grasses, but that's fine. Shrubs 13059. Conifers 33586. Broadleaf 7373. I feel like we could maybe ease off yeah, keep in mind that like the simulation that we're doing for growth in a tile looks very different than someone who's doing a simulation at a very granular level, because this simulation code, complex as it is, has to be replicated over 2 million tiles, right? And that goes back to constraints, right? Like, so we have to view things very differently than if we were doing like literally ground level, tree here, shrub here. Whoa, what is going on this time? Is this just That's crazy. We got totally different results those 2 times. That's kind of fascinating, actually. Ooh, it's kind of what we want, though, too. Interesting. Path shrub. So we need to do 2 things here. Go back to our death equation. Deviation, thirstiness. Where the hell did I put? Where the hell did I put it? Was it? Did I put it after fires? Yeah, I guess I did. Okay. Let's ease off here. Okay, canopy's a bit saner now. Okay, periods of grass. Okay, I think we were being way too punishing to our conifers. Alright, so easing off of the natural death rate, I think improved things for our conifers in this environment, as they should. Because conifers are generally going to be growing slower. And so that downward pressure is pronounced now. Okay, let's go ahead and see what things look like in a temperate forest after we modify these figures. What I really should have is all of these guys in a file somewhere that gets updated each time I run the model. See what the height difference is. Much better. 17, 18, 14. Leaf 6, 2, 5, 5. Okay. All right. Let's now go to temperate forest. Whew. I guess that works. Here we have the succession reset. Yeah, we have periods of very caustic forest fires. I mean, that's cool. I mean, you can see how, like, we literally have 100 years where there's not really a major fire, and you have broadleaf domination. I think it works fine. Let's see how this model holds up now when we... first off, let's replace these values. That's interesting. We have a much higher grass and shrub baseline for temperate forests. which is acceptable. It seemed to have been the case previously too. 12722 9099 7576. Tile conifer canopy average. That seems better. And then 24 meters. That's good. Broadleaf average 26. So almost half of the surface there. Okay. Run it one more time. Yeah, you can see the fires. I don't know, that's a little weird to have. I mean, you literally have succession reset. It's almost has something to do with the random seed or something. I don't know. Let's run it again, see what happens. Maybe it's just a coincidence. Yeah, we shouldn't have this many succession resets. I don't think. How many resets do we have? We have 1, 2. We can count the 1, 2, 3, 4, 5, 6. That's weird. Let's see. So we got 1, 2, 3. Yeah. Looks like the 5. I think it just has to do with being a little too austere here. There's another way to handle this too. We can modify the geometric intensity of fires, which we did where? Okay, here we go. No. 4 conifers. How many fires do we have? 78 intensity. Fire count 35 over 500 years. That seems reasonable. Seems like we get a better mix of conifers when there is a hard reset. I just don't want the hard resets to be like happening all the fucking time. Nice canopy height up there. Seems pretty good. Maybe. Whoa. And sometimes there's gonna be more common than others. Whoops, I think I closed it and I didn't mean to. Intensity, history of fires, 31 fires over 500 years. Okay, so that's once every 15 years. Most of them are not these mega doom fires. Okay. And conifers just don't seem happy in that situation. Which makes me wonder. Oops, try again. Yeah, they got a little more baseline here. Yeah, you have periods where conifers more abundant. It's pretty cool. I like it. I think it works. Let's look at Tegas again. WTF? Okay, something's wrong. Did I put an extra? Yes, I did. Okay. I accidentally made them 114 meters tall at start. Alright, seems reasonable-ish. Uh, 36 fires. Just not as intense. Okay, so here's the trick now. Let's see how we do. We made all these changes. Let's see how the Sahel does. So, boreal forests and temperate forests both have similar seasonal rainfall and water availability. Now let's go someplace that's that has significant seasonal differences. Well, that's interesting. So here's the Sahel. I kind of like it, actually, to be honest. Because so the Sahel is like the African savanna, right? You have sort of trees that are interspersed between each other, and then you have these wide open grassy spaces between the trees. And it can transform pretty often from going to almost exclusively grassland to being, to having quite a few trees. We have a reset event here, you can see. And so we actually have a period dominated by it's like a scrubland. I think it's pretty cool. No, I think it can. I think it can work like this. Let's look at the fire. So fire intensity is 298. And we have a lot of micro fires almost constantly, which is what we want. How many actual fires do we have? 202. 202 over 500 years. So fire just about every other year. I think that's about what we want, actually. Okay. Works. Most of them are so small that they don't really cause much disruption. They're under 1 intensity. Okay, so hell works. Let's look at the Mediterranean, where we should also see these kinds of microfires. But the difference between seasons and rainfall is significantly larger. Yeah, actually, this is about what we would expect, I'd say. Let's look at the spreadsheet. We'll have to modify these values later. Let's go ahead and get a sum of total biomass too. Oops. Okay. So we never reach maximum surface area capacity on the tile. We get to about 40,000, and that's when the fires start to kick in because it just gets not enough water to go around. Okay, mainly shrub dominated. We do have broadleaves. The broadleaves, I'm curious whether they do they ever make like a super long-term decline or anything? Can't really tell. I'm a little concerned about that. Let's go ahead and take these the averages that we have. If we can ever get through the fires here. Mediterranean grass is around 8100. Well, let's be specific. Tile shrubs 23154. Tile conifers. Now, what we want to avoid is a situation where we have, for instance, feedback loops that cause permanent extinction of a vegetation type that should be present in a given biome. So we want some broadleaves, aka things like olive trees and stuff like that, available in the tile. And we can see that, yeah, they survive to some degree. Oh, what's the canopy height? Awesome, exactly what we want. Literally about 6. Oh, did we properly modify our canopy height though? Because in the Mediterranean, you have these very squat little trees. Because no one wants to grow tall and get whipped by the wind and lose all their water, so they grow like almost they behave almost like shrubs. And in the model as it exists, when plants are squat, and there's land area around you to expand to, they tend to try to take up that land area. Anyway, let's see here. Activate clients. Oh, okay, 5. That's fine. Again. Yeah, that's cool. Canopy height is I'd say sufficiently constrained to where we want it to be. Oh, ouch, we had some nasty reset events there. Gross. Okay, we've got a baseline. Let's actually look at the figures. Oh. Let's run this for some crazy amount of time. Let's say 5,000 and see if our broadleaves just end up going extinct long term. Doesn't look encouraging. Now we've logged out so many wildfires we can't get to our averages. Come on. I should probably move that code. Yeah, I don't know. I think our trees are just gradually getting killed off. Move you someplace else. Preferably at the very end. Yeah, I think our broadleaves are gradually getting squeezed to death. Now let's do something even crazier. So we have 316, like virtually non-existent. Let's do 20,000. 20,000 years. No, they're surviving. Okay, so they just have a really, really low baseline. I mean, in some Mediterranean environments like that's just the way it is. Basically coastal scrublands. I still feel like that's a bit low. Well, let's see what else we got here. Can always tune a bit more later. Okay, we got Xeric deserts. We tested Sahel. Tested Mediterranean. Equatorial rainforest isn't going to do much for us. Try the monsoon forest until we have organics, which is like the last big missing piece. We're not going to be able to represent rainforests sufficiently. Canopy growth. Well, that's weird. We we could be having an issue with our monsoon forest for the same reason. Mineral nutrient density is terrible. Yeah, that's gonna. Same here. Yeah. Until we have good organic values. Let's try equatorial rainforest. We're gonna have conifer domination again. What's going on here? Oh. We have so much rainfall and so little mineral nutrients, which means so little growth, that our trees are literally dying faster than they can get to a point where they would cause a fire. Okay, yeah, so that's just, we're not going to get anything interesting there until we have organics in. Similar situation here. Let's try xeric desert. I'm not really sure what to expect here. Okay, low canopy, obviously, because trees should be nearly non-existent. And yes, they are nearly non-existent. This is kind of what we should expect from a xeric desert. Shrub dominated. Not a whole lot of fires because, just a lot of micro fires, which is what we have. That's good. Because the density of the vegetation isn't significant enough to cause, some crazy wildfire. So that's 700 fires. So 700 microfires, that's about what we should want. We probably want to trim back the seed bank. That's kind of the situation where we'd likely want to trim back the seed bank. How many years has this been going on? 500. So 700 fires in 500 years. Alright, so we can see it's not unreasonable. Alright, well, I'm going to call it for now, guys. I'll probably work on it off stream a little bit more, but getting there.